to talk about some work cooperated with Colin and Tomek on a simple model of influence, which shows how network can partition into fragments by following a neighbor. And this can be used to model some influencers and followers' behaviors on social media or some fake news propagation, etc. And in this work, we investigate the influence on a random graph, GNM, which is considered as an involving network where edges are added in a random order. So this is a model for people with some fixed opinions on some topic. And the people kind of, they can join to some other groups if they are influenced by other people. So each group consists of one influencer and their followers. Once the followers join an influence group, they never leave, so they hold their fixed opinion. Equivalently, we can represent these on graphs, which are trees with some edges directed from the children to the root, and the root is the current influencer. So here's a simple example. Suppose we are given a fixed graph G on the right-hand side of the figure, and at the beginning, all the vertices are active, so they're open to be influenced by other vertices. And on the right-hand side is the fragment graph that generated by the process with the underlying graph G. And at the beginning, all the fragments or all the components are individual vertices. Then in every step, an active edge is chosen uniformly at random, and then one endpoint of this chosen edge follows the other end. And an active edge means both endpoints are active. So in the first step, suppose in the graph G, random edge between vertex 2 and vertex 3 is chosen, and randomly vertex 3 follows vertex 2. Then vertex 3 becomes static, so it holds its opinion and never changes from this point. Then on the right-hand side, in the fragment graph, we direct an edge from vertex 3 to vertex 2, meaning vertex 3 follows vertex 2. Then in the next step, we do the same. An active edge is chosen uniformly and random, say edge between vertex 4 and vertex 5. Then vertex 4 becomes static and vertex 4 follows vertex 5. So we direct an edge from vertex 4 to vertex 5 in the fragment graph. And note that vertex 3 has been chosen by to follow vertex 2 in the previous step. So any edges involving vertex 3 is no longer active. Then in step 3, again, a random edge is chosen, say between vertex 1 and vertex 2. Then randomly vertex 2 follows vertex 1, and then vertex 2 becomes static in the graph G. Then in the fragment graph, we direct an edge from vertex 2 to vertex 1. So now the fragment previously rooted at vertex 2 becomes part of the fragment rooted at vertex 1 now. Then in next step, step 4, again, a random active edge is chosen, then vertex 5 follows vertex 1, and we direct an edge from vertex 5 to vertex 1 in graph F. So after this step, the process stops because there isn't any active edge left, and every vertex ends up in the same fragment rooted at vertex 1 for this particular example. So here's the formal protocols. We consider a graph G with n vertices, and each vertex is either active or static. Initially, all the vertices are active and all the fragments in the graph generated from this underlying graph G are individual vertices. And then we consider the edge model as the join rule. So at each time step, a random edge between active vertices is chosen uniformly at random. And the active vertex U contacts its active neighbor V. The order doesn't matter. Just a random endpoint follows the other end. And then the neighbor vertex V follows the vertex U, and vertex V becomes static. Then in the fragment graph, vertex V directs an edge to vertex U, meaning vertex V follows vertex U. And then the vertex V and its fragment becomes part of the fragment rooted at vertex U. There are various models of the different drawing behaviors. So for example, if it's a vertex-based, where a random active vertex is chosen and follows a random active neighbor in each step, or it can be an edge-based, or where the influence groups and the network involving together. This is the same as the previous topic. And the edges of the graphs are added in a random order. If both endpoints of the current chosen edge are active, then one end follows the other. And these different models can give different results on the same underlying graph. And in our work, we consider random graph GNM as an involving network, and we apply the edge model where active edge is chosen at each step. And the central questions that we are interested in, namely the number of the fragments and the case with some stubborn vertices which never follow, and the size of the largest component. So this is the first topic, number of fragments. So suppose the underlying graph is a random graph GNM, and we let capital N equals to N choose 2, and we apply the edge model. Then if for the number of edges M smaller or equal than capital N divided by omega, where omega tends to infinity slowly, then the number of fragments generated by this process is approximately it follows this formula. Then we have a simulation for this theorem. It is plotted based on graph GNM, and this is equivalent to GNM for large M equals to capital N times P. The black points with the blue curves, they are the actual simulation, while the red line is the formula from the previous theorem. And how do we prove this? The idea is that we consider adding edges of a complete graph to an empty graph, one by one in a random order. Then in each step, once an edge is added, one endpoint of this edge becomes static in G. And we stop when there's no edge can be added to the graph. So basically, after N choose 2 many steps. Then after M step, the fragment graph generated by this process is distributed as in the family of the random graph GNM. Then if we analyze the expected change in the number of active vertices in one step, we can get the following recurrence. So the expected value of the number of active vertices at time step t plus 1 is the number of active vertices at time step t minus this term. And this is due to the fact that we have A of t many active vertices at step t, which gives A choose 2 many active vertices. And we only choose one active edge among all the capital N minus t many unexamined edges. Then by a martingale argument, we can prove that the expected value of A is approximately A. And then we used a differential equation method to approximate A, which comes from the top recurrence. Then we can prove that the expected value of A is approximately that formula. Now I'd like to clarify a bit of the evolving GNP and the static GNP. So in the evolving GNP, it is modeled as GNM with M equals to N choose 2 times P, and the expected number of influencers, or the number of the fragments in the end, is approximately 2 over P, which is from the previous theorem. And in the static GNP, where a random active vertex is chosen follows a random active neighbor in each step, the expected number of influencers in the end is approximately 1/p, so it's half of the size. I'll only give a brief sketch of how to prove the previous statement. So in the involving GNP, we have m equals to capital N times P. Then from the previous theorem, we have the expected value of the number of influencers after m step, which is this much. Oops. It happens to me again. Thank you. So we have this formula, and we know that m divided by n is p. Then square root of 1 minus p is 1 minus p over 2. Then this whole term is approximately 2/p. Well, for the static GMP, initially we have n active vertices, and the number of these active vertices decreases by 1 at each step. Then after t steps, we have n minus t active vertices left. If we let s be the number of the static vertices at step t, then at the beginning, every vertex is active. So S0 is 0. And then the expected change in the number of static vertices in one step is 1 minus p to the power of n minus t minus 1, which is the probability that the chosen vertex doesn't have any active neighbors. Then if we sum up this term from all the from step 0 to step n minus 1, this gives us the final number of active vertices, which are about 1/p. Now the second topic, in the case that there are some stubborn vertices. So stubborn vertices are those who accept followers but refuse to follow, just like dictators. If we let k be the number of stubborn vertices, then when k equals to 1, there's only one stubborn vertex. And if m equals to c times capital N, where c is some constant between 0 and 1, then one single stubborn vertex reduces the number of influencers by a factor of square root of 1 minus c. And if k tends to infinity slowly with n, then there will be no independent influencers remain, even if for large m equals to capital N divided by omega. Here's a simulation which is also based on GMP for convenience, and it's equivalent to GNM for large M. So here the blue data points is they are the number of the active nodes, and P varies from point something to 1. And the green line is the number of the independent active nodes, so without the stubborn vertex. We can see that with this one stubborn vertex, it reduced the number of the independent active nodes. If there are 5 stubborn vertices, here the green lines, it's the number of the independent active nodes, and the red line is the number of the independent active nodes plus the number of the stubborn vertices, which is 5. And the blue line is just for comparison in the case if there's no any stubborn vertices. And we can see that if there are stubborn vertices, the number of active nodes, they decreases a lot. So when this number of stubborn vertices, they tends to infinity, there will be no independent active nodes left as P increasing. The third topic is the size of the largest component. So we let k be equals to a of m, which is a random variable. And from the previous topics, we know that for G and M, the expected value of the number of active nodes or the number of components in the fragment graph is about 2m divided by capital N, where capital N is n equals 2. So if a random graph GNM is separated into k fragments, then the size of the largest component is about n log k divided by k. Here's another simulation. So the blue data points in the middle is the average largest component size over 2 replications. And note that on the y-axis is the proportional size of the largest fragment, which is the number of largest component divided by n. And the upper blue curve is log k divided by k, which is just this formula divided by n. And the middle diagonal black line, just for comparison, is y equals to x. And the blue curve is 1 over k, the average component size. And the idea to prove this is we try to relate it back to the stick breaking process. So we consider m equals to capital N. So the underlying graph would be a complete graph, in which case the fragment graph consists only one component after capital T many steps. So if we consider going backwards for one step, then at step T minus 1, there will be two components. They are drawing via one active edge chosen at this step, and then they merge into one component in the next step. So we don't know the sizes of these two components, but we do know that the size add up to n. So this is equivalent to dividing one component of size n into two random components. And if we go back for k many steps, this gives k plus 1 many components. And this is equivalent to a stick breaking problem, where you are given a stick of length 1, and then you want to divide it into several pieces. And the distribution of the size of each component or each several sub-pieces is well studied. So today we've talked about a model which is simple and depends only on the connectivity of the involving network. And this also allows for the inclusion of stubborn vertices, and it can measure their distorting effect. For the further work, we can consider adding some features to the, for example, to the drawing rule. So an edge being accepted with some probability, they don't always get accepted. Or we can consider some divided society where there are two types of vertices, red and blue. Then the probability of a red node follows a red follower is far larger than the probability that of a red node follows a blue node. Or we can consider the bottom where vertices can stop following and becomes an active influencer for their subgroup, where with some probability at each step. Yeah. Thank you.
Thank you very much.